In this lesson, we will master the foundations of complex numbers, a topic that is essential for both standard and higher-level students in the IB Analysis and Approaches syllabus. We will cover the Cartesian form, the geometry of the Argand diagram, and the essential operations of addition, multiplication, and division. These concepts frequently appear in Paper 1 as part of larger algebraic problems, and in Paper 2 when utilizing technology. Mastering these basics is the key to securing high marks in the more advanced topics of de Moivre's theorem and Euler's form. Let's begin with the definition. A complex number is an extension of our real number system. It allows us to solve equations that previously had no real solution, such as x squared plus 1 equals 0. To do this, we define the imaginary unit I such that I squared equals -1. This implies that I is the square root of -1. Any complex number z can be written in Cartesian form, which is a plus bi. Here, a and b are both real numbers. We call a the real part of z, and we call b the imaginary part. It is vital to remember that the imaginary part is just the real coefficient b, not b times I. Consider the example z equals 3 minus 4i. The real part is 3. The imaginary part is -4. We can represent complex numbers geometrically using an Argand diagram. This is essentially a coordinate plane where the horizontal axis represents the real part and the vertical axis represents the imaginary part. The complex number z equals a plus bi is represented by the point with coordinates a, b. Another key concept is the complex conjugate, denoted by z star. To find it, we simply change the sign of the imaginary part. So, if z is a plus bi, then z star is a minus bi. Geometrically, this is a reflection of z in the real axis. This property is particularly useful when dividing complex numbers, as we will see shortly. Every complex number has a magnitude and a direction, similar to a vector. The magnitude is called the modulus, denoted by the absolute value of z. It represents the distance from the origin to the point in the complex plane. By applying Pythagoras' theorem to our Argand diagram, we find that the modulus is the square root of a squared plus b squared. The direction is called the argument, which is the angle theta that the line from the origin to z makes with the positive real axis. We find this using trigonometry, where the tangent of theta equals b divided by a. In the IB, we focus on the principal argument, which is restricted to the interval between -pi and pi. It is critical to check which quadrant your complex number is in before calculating the argument. Let's find the modulus and principal argument of z equals -1 plus I root 3. First, the modulus. -1 squared plus root 3 squared gives us 1 plus 3, which is 4. The square root of 4 is 2. Now for the argument. The point is in the second quadrant. Because the real part is negative and the imaginary part is positive, we first find the reference angle alpha by taking the inverse tangent of the absolute values, which gives us pi divided by 3. Since we are in the second quadrant, the argument theta is pi minus the reference angle. This gives us a principal argument of 2 pi over 3. Now let's look at basic operations. Addition and subtraction are straightforward. You simply combine the like terms. Z sub 1 plus Z sub 2 equals a plus c plus b plus di. Z sub 1 minus Z sub 2 equals a minus c plus b minus di. This means you add the real parts together and then add the imaginary parts together. Think of it like vector addition in the complex plane. For multiplication, we use the distributive law, often called FOIL. Z sub 1 times Z sub 2 equals AC plus ADI plus BCI plus BDI squared. The most important step is substituting I squared with -1. By doing this, the term with BDI squared becomes -BD, which is part of our new real part. Division is slightly more complex. We cannot have an imaginary unit in the denominator. To remove it, we multiply both the numerator and the denominator by the conjugate of the denominator. z sub 1 over z sub 2 equals z sub 1 times z sub 2 star over z sub 2 times z sub 2 star. This process, similar to rationalizing a surd, results in a real number in the denominator because any complex number multiplied by its conjugate equals a squared plus b squared. Let's simplify. 1 plus 2i divided by 3 minus I. We multiply the top and bottom by the conjugate of the denominator, which is 3 plus I. Multiply the numerator and denominator by 3 plus I. The denominator becomes 9 plus 1, which is 10. In the numerator, 2i squared becomes negative 2. This simplifies to 1 plus 7i over 10. This gives us a real part of 1/10 and an imaginary part of 7/10. Let's apply these skills to an authentic IB-style question. Suppose we are given two complex numbers, z1 equals 2 plus ki and z2 equals 1 minus 2i, where k is a real constant. We are told that the product, z1 times z2, is purely imaginary. Our goal is to find the value of k and then express the quotient, z1 divided by z2, in Cartesian form. First, we find the product. Multiplying the terms, we get 2 minus 4i plus ki minus 2ki squared. Recall that I squared is negative 1, so the last term becomes plus 2k. Now, let's group the real and imaginary parts. The question states the result is purely imaginary. This means the real part must be 0. Solving 2 plus 2k equals 0, we get 2k equals negative 2, so k equals negative 1. Now we substitute k back into z1, so z1 is 2 minus I. To find the quotient, we multiply by the conjugate of z2, which is 1 plus 2i. Expanding the numerator gives 2 plus 4i minus I minus 2i squared, all over 1 squared plus 2 squared. This simplifies to 2 plus 3i plus 2 all over 5, which equals 4 plus 3i over 5. In an exam, always separate your final answer into distinct real and imaginary parts, as shown here, 4 over 5 plus 3 over 5i. Common mistakes. Let's discuss how to avoid losing marks. One of the most frequent errors is misidentifying the imaginary part. Consider the complex number z equals 3 plus 5i. The imaginary part of z is 5, not 5i. Remember, the imaginary part is just the real coefficient. If you write 5i instead of 5, you will likely lose the accuracy mark. Another common pitfall occurs when calculating the argument. Many students simply use the inverse tangent of b over a without checking the quadrant. If z is negative 1 minus I, the tangent of theta is negative 1 over negative 1, which is 1. However, the angle theta is negative 3 pi over 4, not pi over 4. If z is negative 1 minus I, it lies in the third quadrant. Using the formula blindly might give you pi over 4, which is in the first quadrant. Always sketch a quick Argand diagram. Lastly, be careful with signs during multiplication and division. A common mistake is forgetting that I squared equals negative 1, which flips the sign of the constant term. Exam tips. In the IB exam, examiners look for clear methods. When dividing, always show the step where you multiply by the conjugate, even if you make an arithmetic error later. This step earns you the method mark. If you are sitting paper 2, ensure your calculator is in radian mode. Complex number arguments in the IB are almost always expected in radians, unless degrees are specifically requested. Finally, use the property that the modulus squared is equal to z times its conjugate to quickly check your modulus calculations. Now it is your turn to practice. Please pause the video and attempt these 3 questions. Easy. If z equals 4 minus 3i, find the modulus and the complex conjugate. Medium. Express 2 plus I divided by 1 plus 2i in the form a plus bi. Hard. Find the 2 possible values of the real constant p, such that the modulus of p plus 2i squared is equal to 25. Take a moment to solve these before we move on to the solutions. Let's go through the solutions. For the easy question, z equals 4 minus 3i. The modulus is the square root of 4 squared plus negative 3 squared, which is the square root of 25, giving us 5. The conjugate, z star, is found by flipping the sign of the imaginary part, so it is 4 plus 3i. For the medium question, we multiply the top and bottom of 2 plus I over 1 plus 2i by the conjugate of the denominator, which is 1 minus 2i. Expanding the numerator gives 2 minus 4i plus I minus 2i squared, and the denominator becomes 1 squared plus 2 squared. Simplifying the top, since I squared is negative 1, we get 2 minus 3i plus 2, all over 5. This results in 4/5 minus 3/5 I. So A is 4/5 and B is negative 3/5. For the hard question, we need the modulus of the squared expression to be 25. A useful property here is that the modulus of z squared is the same as the modulus of z, all squared. This implies that the modulus of p plus 2i squared equals 25. Therefore, the modulus of p plus 2i must be 5. The modulus of p plus 2i is the square root of p squared plus 2 squared. Squaring both sides gives us p squared plus 4 equals 25. Subtracting 4, we get p squared equals 21. So, p equals plus or minus the square root of 21. These are our two possible real values for p. To summarize our lesson on the foundations of complex numbers. First, always remember the fundamental definition that I squared equals negative 1. This is the engine that drives all complex number algebra, especially in multiplication and division. Second, the Cartesian form z equals a plus bi consists of a real part a and an imaginary part b. Crucially, the imaginary part is the real coefficient b, not including the I itself. Third, understand the geometry. The modulus represents the distance from the origin in the Argand diagram, and the principal argument is the angle measured from the positive real axis, restricted between negative pi and pi. Fourth, when dividing complex numbers, multiply the numerator and denominator by the complex conjugate of the denominator to rationalize the expression. Finally, never calculate an argument without first sketching the complex number. This ensures you correctly adjust your angle based on the quadrant in which the number lies.